So welcome everyone to this Meet GERAD Researcher webinar. Today we have the pleasure to welcome Professor Marie Kang from McGill University for a presentation entitled Mitigation and Management of Climate and Environmental Impacts of Abandoned Oil and Gas Wells. But before this presentation, I will let Marie introduce herself and present as well her research interest.
Thank you so much for for organizing this and inviting me to talk today. I'm very excited to be here. So I'll just give a little background about myself. So my research area broadly is climate and environmental impacts of subsurface-based energy development and urban activities. So it's much broader than what I'm going to be spending most of my time talking about today. I will touch on a few other things that I also am working on. So just in terms of my background, before arriving at McGill in 2018, I was at Stanford as a postdoctoral fellow in the Earth System Science Department. And then before that, I did my PhD in civil and environmental engineering at Princeton University. I did a policy certificate at the Princeton School of Public and International Affairs. I did a exchange or a semester at the University of Bergen. And then before that, well, I worked in between as a consultant. And then before that, I did my master's and my undergrad at the University of Waterloo. For my undergrad, I did very traditional civil engineering, but for my master's, I did more, I did groundwater modeling. And for my PhD, I looked at geologic modeling looking at leakage in the case of geologic storage of carbon dioxide. So a lot of my research overlaps with GERAD's research axis and themes. In particular, in axis 1, I do mathematical modeling. And of course, it comes with that model identification and state estimation. Right now, actually, I spend a lot of time doing data mining. And so that has because that has become an increasingly important part of what I do. And along with that, statistics and more recently looking at machine learning and artificial intelligence to treat and analyze that data. And of course, simulation. And in terms of the application areas, kind of what I've mentioned before, so energy systems, environment, and natural resources are the natural fit. And of course, I'm in engineering. So that brings me to my research topics, which I've alluded to earlier already. So what I'm going to spend most of my time talking about today are abandoned oil and gas wells, specifically methane emissions and other environmental impacts. Some of my research questions are, how many abandoned oil and gas wells are there? How much methane does an abandoned well emit? What are the attributes of high emitting wells? And how can we reduce methane emissions and other environmental impacts from abandoned wells? And then two other research topics that I'm working on right now, but that I'm not going to spend too much time talking about are groundwater quality, quantity, and protection, and methane emissions in Montreal. So I've mentioned methane a few times already. So I wanted to just, for those of you who are not familiar, just talk briefly about why methane is important or why we care about methane. So methane is a greenhouse gas. So it's a potent greenhouse gas. It is estimated to have a global warming potential 28 to 36 times that of carbon dioxide. And that's over 100 years. So if you look at shorter time spans, like 20 years, that global warming potential is much higher. It's 86 times that of CO2. And it's actually even much higher if you look at even shorter time spans. So if you look at, so this pie chart here shows you a breakdown of greenhouse gas emissions estimated from anthropogenic sources in Canada. And this one uses a global warming potential of 25, so even less than this 28 and 36 that I mentioned. And you can see largely it's CO2, it's 80%. It's 13% methane, but again, it's using a lower global warming potential. But it's still an important, even if you use 25, it's still a very important part of that pie. And it's going back to this time frame issue. Methane is also very interesting or important to reduce if you want to have impacts in the short term. So there are many sources of methane. I'm going to go over some of them later, but the sources that I'm particularly interested in are abandoned oil and gas wells and urban emissions. So what are abandoned oil and gas wells? I'm going to provide a definition shortly, but what are they in and how do they impact methane emissions and groundwater contamination and lead to groundwater contamination? So what I'm showing here is a diagram or a schematic of what you would see if you take a slice through the earth in sedimentary basins where you would typically find oil and gas. So what you would see are layers of rock containing different types of, with different properties and containing different types of fluids. So these gray ones here would be oil and or gas formations. Okay, and there could be multiple on top of each other. They're often separated by relatively impermeable layers that prevent flow from moving between these different formations. And then at much shallower depths, you typically have groundwater aquifers, which is an important source of water for all agricultural, domestic, industrial uses. So one of the important things is that you want to protect groundwater aquifers, and these wells become a concern for contamination because they provide a conduit for oil and gas to migrate upwards into groundwater aquifers and gases to be emitted at the ground surface. There's something called plugs. So there are technology or there are methods to prevent such contamination, which I'm going to talk about later. So groundwater contamination is a concern, and it is an area that I am looking at, but largely what I'm going to be talking about are gas emissions at the surface. And there are other gases that are emitted as well, but methane is the main one that I'll be talking about today. So what is an abandoned oil and gas well? The definition varies among states, provinces, territories, and countries. And at every one of those levels, it depends on which agency you're with. So even in a given state, for different agencies within a single state, you may have different definitions. But today I'm going to be using the definition by the U.S. Environmental Protection Agency and the U.S. Greenhouse Gas Inventory. So the term abandoned wells encompasses various types of wells with no recent production and not plugged. Common terms such as those used in state-based databases might include inactive, temporarily abandoned, shut-in, dormant, and idle. Wells with no recent production and no responsible operator. Common terms might include orphaned, deserted, long-term idle, and abandoned, and wells that have been plugged to prevent migration of gas or fluids. So what do they look like? Here are some pictures. So a lot of these are in Pennsylvania, where I started my work. And so they all look a little bit different depending on where you are in the world. But what I want to show is that some areas you actually have these, they're not plugged. The wells have just been left for decades, maybe even a century, and you still have some steel casing there, as you can see in these cases. Some places have infrastructure still at the ground surface, above ground, and some places it's just basically a hole in the ground. So in this case, the landowners put a tire and sticks on so people or animals won't fall in. And then there are these wells that are plugged, which I briefly mentioned earlier. And so these are actually markers just to show where the plugged wells are. A lot of places, including most places in Canada, do not have such markers. And so you would see no surface evidence, except for maybe slightly different vegetation, but you won't know exactly where the wells are. So how big is this problem? How many abandoned oil and gas wells are there? Turns out there's a lot, especially in Canada and the US. And these numbers are not well defined. So globally, there's likely to be tens of millions, but there hasn't been a good estimate so far. This is an area that I'm actively working on. So in the US alone, there's more than 2.5 million abandoned oil and gas wells. And you can see, these are all wells, but it kind of follows the same distribution. And you see a lot in Texas. This is Appalachia. You have Oklahoma, California, and of course in Canada, Alberta is a big hotspot. And you can see the breakdown here. Alberta has 67% of the wells in Canada, followed by 20% in Saskatchewan, 5% in BC. And in the US, Texas, Pennsylvania, Kansas, West Virginia, Oklahoma, these are some of the top states, which I've highlighted here. Just in terms of numbers, in Canada, there are probably around 450 to 500,000 abandoned wells. So these are abandoned wells, so there have been more wells that have been drilled. And so at some point, those wells will also get abandoned. So I didn't provide an exact number. I said more than 2.5 million or 450 to 500,000, because there's a lot of uncertainty in the number of abandoned wells that exist, and some places more than others. So Pennsylvania is particularly, it has a lot of uncertainty, more than others, or possibly more than others. As one of the reasons is because it has the longest history of oil and gas production. So the first commercial oil well was drilled in Pennsylvania in 1859. So that was number one here, first well. And since then, there have been several peaks in production. This data only goes up to 2014, but you can see there was a big peak in production in the 1880s, another in the 30s, another in the 1980s, and then more recently with shale gas development. And then if you look at different sources of data, they appear to match quite well. But especially the historic data, there's a lot of uncertainty. And what's interesting is if you go into the field and you use this database or data source and you go into the field and there's supposed to be one well, but then you end up finding 20 or you find none. And there's just a large uncertainty. So based on a lot of data mining and data analysis, there's possibly 450,000 to 750,000 abandoned wells in Pennsylvania alone. So going back to methane, how much methane does an abandoned well emit? So when I started working on this in 2012, 2013, turned out there were no measurements of methane emissions from these wells. So I got a team together to do these measurements. And so we used what are called flux chambers or enclosure-based methodology. And we took gas samples, which were analyzed in the lab for methane, ethane, propane, and butane. We also looked at isotopes. Isotopes and also noble gases. And all this geochemical data gives you more information about where the gas is coming from. And of course, we want to quantify how much methane is coming out of these wells. So this is from my first study on this topic. And basically what we found, is that there's definitely more methane coming out of the wells than the control areas. So like 5 meters away, I also did the same kind of what are called chamber measurements to look at emission rates. And you can see, so the red and orange lines represent measurements at wells, and the green lines represent kind of background emission rates. And this is, so each of these are a single measurement. And this is the methane flow rate. So the mass of methane being emitted to the atmosphere per unit time and location. And the positive numbers mean methane is being emitted into the atmosphere. So you're contributing to methane in the atmosphere. And negative numbers means it's a sink of methane. So the microbes in the soils, for example, are pulling methane from the atmosphere and consuming it. So what you see here is, and this is again orders, this is in orders of magnitude, and you're seeing at the wells, you're seeing it's all positive sources of methane from 10 to the -1 to 10 to the 5. Whereas in controls, they can be sources of methane, but it's generally much lower. And in many cases, in about half of those cases, it's actually a sink for methane, which is what we know about forest soils. And similarly for grassland, we see the same thing. For wetland, as you can see, we know wetlands are sources of methane to the atmosphere. So you can see the background always, they're always emitting methane. But again, the emission rates are much lower than at wells. Another really interesting finding from this just very early study is the difference between the red and orange bars. The red bars are these unplugged wells, and the orange bars are the plugged wells. And so plugged wells should theoretically emit no methane or be just basically the same as controls. But that's not what we're seeing. As you can see, they're not the highest, but they are high, and they're generally statistically higher than the emissions coming out of the controls. So I mentioned geochemistry a bit because this kind of information tells you at what depth the methane is coming from. So if you see ethane, propane, and butane, it means that the methane that's coming out is likely to be coming from a thermogenic source, so somewhere deep under the ground, and like oil and gas formations. If you don't see ethane, propane, and butane, it means that it's more likely to be coming from a microbial source, so methane being produced by microbes, like for example in wetlands. So, but as you can see clearly, there's these are the bars. This is all the data and the range of data for controls, and then the hatch represents wells. And you can see there's just a lot more ethane, propane, and butane coming out of the wells than at the controls. So this is isotopic data. So the same kind of thing, but instead of looking at ethane, propane, and butane, which are higher change alkanes, we also looked at isotopes, so stable carbon isotope of methane. So if you have a more negative value, then it's likely to be a thermogenic source. And if you have a more negative value, then it's a microbial source. Less negative, then it's thermogenic. So you can clearly see the wells are the diamonds, the gray diamonds, and the controls are the open squares. And you can see that the wells are more likely to be in the thermogenic, although there's a few in microbial. Another interesting is if you look at the scale of the methane flow rate. So the highest emitters, as you can see, 10 to the 3, 10 to the 5, these are almost always in this thermogenic range. So they're coming from deep formations. So is this a periodic thing, or does this happen for years? This is also another active area of study. Basically, what we find is that we measured wells over 3 years, some of them up to 10 times over 3 years. And in general, we're finding that high emissions continue for multiple years and possibly decades. So this is the methane flow rate. So for the higher methane flow rates, the coefficient of variation, so just standard deviation divided by mean, is much lower than for the lower methane flow rates. So another important thing here is that if you look at the emission rates or methane flow rates that I've shown, so they vary considerably by 7 orders of magnitude, 8, 9 orders of magnitude or more. So some are emitting almost nothing and some are emitting a lot. But the atmosphere doesn't care if the methane emissions come all from one source or some from many sources, but at a lower rate. They just care about the total emissions. So the high emitters are the ones that are important when you're thinking about methane emissions, because that's what we need to know. That's what's important when we're thinking about climate and also air quality impacts. So you can see that the median and the mean are, more than 2 orders of magnitude apart. And so these high emitters in the 10 to the 4, 10 to the 5 milligrams per hour per well, they really govern the total emissions. So what that means is, if you're thinking about mitigation, or even if you're thinking about what are the total methane emissions, you need to figure out which wells are high emitters. So that is the next question. What are the attributes of high emitting wells? How can we find these high emitting wells? So with that goal in mind, we went back out to the field to measure different types of wells. So we did look at plugging status and plugged versus unplugged. And we also looked at some other variables as well. But this one here, what this shows, so we're not showing any controls here. These are just wells. You have the positive values of methane flow rate, so emissions to the atmosphere, -1 sinks of methane from the atmosphere. BD stands for below detection. Again, orders of magnitude variation. So the blue bars here represent methane flow rates at individual abandoned gas wells. And the red ones represent measurements of methane flow rates at oil or combined oil and gas wells. And as you can see, the blue bars are all or are likely to be higher than the red ones, but the highest bars are all blue. So high emitters are more likely to be gas wells. Another thing that we did is we separated the data. So this data set here are measurements at unplugged wells. This data set here, so let's ignore this for a minute. This set of measurements are at plugged wells. And as you can see, plugged wells, you go up to almost 10 to the 4 milligrams per hour. But for unplugged wells, we're much over 10 to the 5. So in general, unplugged wells emit orders of magnitude more methane than plugged wells. However, there is this special category of plugged wells called plugged and vented wells, shown here. And these wells are in coal areas, and they're required to be vented by regulation. And as you can see, even though they're plugged, they emit as much methane as the unplugged wells. So those are just a few factors, but there could be other factors. What about depth? What about distance to nearest natural gas storage field or active unconventional well? What could those other factors have an impact in addition to plugging status and well type? And there's different ways to look at coal area designation. So coal area designation matters because if you look at coal area designation and plugging, it could tell you whether the well is plugged and vented or plugged but not vented. So what I showed you before. So what we did was we took that data and we did a bunch of multilinear regression analysis to figure out which are the important variables. And we basically see kind of what I showed you in the previous figure, that the coal area designation matters, plugging and well type, these are the variables that matter the most. We didn't find a significant relationship with depth, distance to nearest underground natural gas storage field, or distance to nearest active unconventional well. Having said that, it doesn't mean that those variables are not good predictors of high emitting abandoned wells, but it's also, we have a limited data set. But the other big question is, are we missing other important factors? So in a recent study, we looked at geographic variation. So now we have a bigger data set, that 598 direct measurements that have been made across Canada and the US. And so we again consider the different categories: gas, oil and gas, plugged and unplugged. And then we looked at Western US. So we looked at it by state: Colorado, Utah, Wyoming, Eastern US, Pennsylvania, West Virginia, Ohio, Oklahoma in the Southern US, and Canada, BC, and New Brunswick. And what you can find here is that the distributions do vary depending on where you are. So there is some variation, and in some places, the variations can be quite significant. And so, so from that, geographic variation is important, but there's many other factors that may be predictors of high emitters that we have not yet looked at. And so we're working hard trying to do a lot of data mining to get this data to understand what other factors may be important predictors of high emitters. So what does this all mean? How much methane is emitted from these abandoned oil and gas wells in the US and Canada? In the US, so these are the methane emission sources, are anthropogenic methane emission sources in the US. The Canadian one is roughly similar. The number one methane source in the US, anthropogenic methane source, is enteric fermentation, so cows. And then the second one is natural gas systems, then landfills, coal mining, manure management, petroleum systems, wastewater treatment, rice cultivation, stationary combustion, and abandoned oil and gas wells comes in around a 10th place. So it's not the biggest, but it is still, it's still an important contributor. But one thing that's important to look at is if you look at the emission estimates, okay, so it comes in 10th, but if you look at the uncertainty range, it could easily move up a level, 1 or 2 ranks, because the uncertainty bounds are the biggest, from -83% to 215%. You can see if you compare it to other numbers, it's the largest. And these uncertainty range estimates don't account for all the types of uncertainty that exist. And so, it can be a lot larger. So we did some analysis as well to see, okay, how good are these means? And, what information, so what we did was we integrated geographic variation a lot more, and also put in the impacts of plugging status, gas versus oil. And we did a bunch of different scenarios to estimate methane emissions from abandoned oil and gas wells in the United States and Canada. So the blue bars are estimates that we did with our uncertainty range estimates. And this is the US EPA report. And then the red bars here are for Canada. So these are our estimates. And this is the estimate from Environment and Climate Change Canada. As you can see, the blue bars are a bit higher than the white, but the red bars are quite a bit higher than the white here. So in fact, in the US, the inventory is likely to be underestimating methane emissions from abandoned oil and gas wells by about 20%. But in Canada, it's underestimated by about 150%. So how can we reduce methane emissions from abandoned wells? So now I'm just going to talk a bit about plugging here. So we have these different layers of rock containing different types of fluid. and you have a well that's drilled through and connecting so that you can get oil and gas to the ground surface. But of course, if there are any issues with the well integrity, then you could have leakage into saline water and groundwater. So to prevent that, you would isolate zones. You would isolate zones along zones where there's protected water. So protected water is something that's defined in regulations, typically fresh water or whatever is considered usable, which is in itself is a definition that varies substantially depending on where you are and who you're talking with. And then, of course, you also want to preserve the oil and gas reservoir, so you would plug that as well. So the plug material is typically cement. And at the surface, there's different, depending on where you are, the rules are a little bit different, but in general, the wells are cut below ground and buried, and with no surface indication of well location. But in places like Pennsylvania, they do have surface markers. So it depends on where you are. So largely, as I showed before, plugging generally, even this with cement, which is, not with the newest technology, it's kind of the same technology that's been around for decades, but they seem to reduce methane emissions by at least, order 1 or 2 orders of magnitude, which is important. But one of the biggest barriers here is cost, because plugging costs can be relatively high. So the average plugging costs are around $10,000 to $100,000 per well. And the regulations require companies who benefited from the well to plug the well. And that's generally true across Canada and the US. But there are a category of wells called orphaned wells, where a responsible party no longer exists. And in these cases, typically governments are responsible for plugging. And in some states and provinces, there's quite a few of these wells. So in Pennsylvania has hundreds of thousands of orphaned wells that the state cannot plug. And they're plugging something in the order of, 30 wells per year, 20, 30, 50 wells per year. So they do not have the funds to plug a lot of these wells. So the plugging costs become a huge barrier, and the plugging costs are highly variable. And these are for, they have changed over time. And it's not clear that they've been going up or down, depending on where you are, because there's quite a bit of variation. But in general, they're around, in the order of tens of thousands, 20, 30,000 is a good average for the United States. In Canada, average plugging cost is around 60,000 Canadian dollars per well. But the costs are highly variable. These are average plugging costs. So this red square represents the average plugging cost for Pennsylvania in 1992. And so if you look at the data, so this is not the exact same data set, but these are a set of wells that have been plugged by the state and how much it costs them. So this is now, the scale is quite different. So you do get, the average is around 20,000 or 30,000, those are for all wells. But if you look, some can be as high as over 200,000. And actually more recently, there are some that are up to $1 million. And then there's another important thing, is that if you look at all wells versus just gas wells, which are a subset of all wells, they tend to be higher, even in terms of average, by another 10, 20,000. And that actually makes a big difference, because it might prevent a well from being plugged altogether. So to figure out what are the best mitigation options and what to do about them. So plugging is an important component because it's required by regulation. But there are many wells that remain unplugged. So what can we do about those methane emissions? Well, in terms of commercially available mitigation options, you can vent it, or you can flare it or use it. And so so what's done here is we looked at a bunch of different commercially available mitigation options, considered all the different types of costs associated with plugging the well, and also consider something called the social cost of emitting methane. So there's different social costs. This SCM, social cost of methane, is from the US government, what they use in their policy analysis. And this one, social cost of methane, including air quality and other impacts, is another estimate, and which is much higher. And so depending on what you use, you can see that there's the net cost of mitigation options could be positive or negative. So in general, with the social cost of methane, without including air quality and other environmental impacts, you're going to get negative costs. Whereas if you include air quality and other impacts, you'll get all positive. So mitigation options for methane emissions from abandoned wells are not limited to plugging. And if you consider the full social cost of emitting methane, plugging results in net savings. As you can see, all the black bars in the positive area. So to sum up, climate and environmental impacts of abandoned oil and gas wells require data analysis to understand the scope of the problem and develop cost-effective mitigation strategies. Even if society transitions away from fossil fuels and all active production stops, these abandoned wells will continue to impact our climate and environment. So I'm going to spend just a few minutes to quickly talk about groundwater quality, quantity, and protection, and also methane emissions from Montreal. Just a few news articles from some of my publications. So big data offers promise of better groundwater management in California. So in this, to the article to the right, talks about analyzing over 200,000 groundwater samples to better understand what water should be managed under their Sustainable Groundwater Management Act. Because right now, a lot of the groundwater sustainability agencies are using data, or actually not data, but data compilations and analysis that were done in the 1960s and 70s. And so this is one story. Another story that kind of connects us to the oil and gas topic that we've been talking about is what water should be managed and protected. So one of the things is that as you go deeper under the ground, groundwater becomes more saline, and people historically said, okay, that's not usable. But technologies have been changing, and desalination is now much cheaper than it used to be. So there's a lot of water that's now quite economical to actually use in places like California, where and during drought. But this water is not necessarily protected. And so based on regulations from the past, oil and gas activities could happen in some of these groundwater aquifers that may now be usable. So there is a lot of concern about oil and groundwater contamination. This is particularly concerning because if you look at oil and gas well distribution in California, these are where a lot of wells are found. And if you look at where the critically overdrafted groundwater basins are, you can see, especially the southern Central Valley here, that's where a lot of oil and gas wells are located. So just a few words about methane emissions in Montreal. So this is, we've been doing this since 2019 for 2 years. We've been measuring methane emissions from natural gas distribution, landfills, and other sources across the city. Because current estimates of methane emissions made in Montreal are actually not based on any measurements made in Montreal. There are measurements based elsewhere using something called emission factors. And so that leads to a lot of uncertainties. And so really, to develop effective methane emissions reduction strategies, we need a measurement and data-driven analysis. So just to summarize, my key areas of research are abandoned oil and gas wells. To answer questions like, how many oil and abandoned wells are there? How much methane does an abandoned well emit? What are the attributes of high emitting wells? How can we reduce methane emissions and other environmental impacts from abandoned wells? And we talked about groundwater quality, quantity, and protection. And I'm interested in methane emissions in urban areas. Right now, I've been focusing mainly in Montreal. And I'm very happy to make this presentation today because I'm really looking forward to building new collaborations through GERAD to apply operations research, decision analysis, data mining, and machine learning to these environmental engineering problems. Thank you.
Thank you, Mary. Very interesting presentation. We do have some time for questions. So if you have a question for Mary, please go ahead. I'm not sure you were hearing me correctly. Sorry. So I was just saying thank you very much, Mary, for your very interesting presentation and opening the floor for questions from the audience. I may have one. You were mentioning that you are interested in urban emissions. So can you just detail a bit what type of studies you consider at the urban scale?
Yeah, so we've been looking at, so we actually collaborated with Environment and Climate Change Canada. And so we did vehicle-based surveys of methane. So we have laser-based sensors on vehicles, and we drive around, account for wind speed, et cetera, and look at concentration mapping to figure out what sources are. So we're doing that, but we also do the same kind of chamber-based methods that I showed you that we did at wells to quantify emission rates. So we're working with Énergir and ECCC to do some of that work right now. So we're looking at natural gas distribution, various throughout all of the throughout Montreal. We're looking at a lot of landfills, but of course there's wastewater treatment plants. So we just carry around different sensors, and then there's different scales of measurements. You could do it at a kind of like at the ground level scale, where you have to actually go to the source, or you can do it at kind of farther away and then do some kind of atmospheric transport chemistry model. And so we're doing multi-scale measurements. I don't know if that answers your question.
Yes, it does. Yeah. Thank you.
We're also doing a lot of analysis because we got using, for example, natural gas distribution. We have to do a lot of data analysis because we have the full network. And then we can determine, well, how many of such a component are there? Okay, so then we have to make sure, okay, we probably want to measure more of these and less of these. And then we'll put all that information together to come up with an estimate for the city.
All right. Roussos, you have
I have two small questions. Yes.
Go ahead.
My first question follows from the previous one. I'm wondering, I don't really know almost anything about how the data you collect in cities, would they be spaced in different locations and taken at different times? So would you have some sort of a time-space data set?
Yes. So it has to be, we do geospatial and temporal analysis. So there are some components that are likely to be emitting more at a constant rate, and there are other ones that are likely to be more event driven. So we're not likely to necessarily catch all of them, but that's why we have these multi-scale measurements. And we're also planning to put a eddy covariance tower. So you put a fixed tower with collaborators at the University of Montreal, and then you can see it's a fixed location, but you can see how things change over time. So methane emissions at landfills, for example, will vary with seasons naturally because it depends on the microbial activity. So in those places, we're definitely doing seasonal measurements. And then we also walk around to find hotspots. So we'll walk around with a sensor to find hotspots. We'll drive around with sensors as well. So and we also have some drones to fly around to get different screening. So this is multi-scale measurement system along with a good understanding of the infrastructure data. So you have to know where the natural gas distribution lines are. you have to know where the different infrastructure is to estimate how much is coming from them. And then we do some spatial temporal analysis.
Okay, thank you. I have one more question if there is time, but I think there are more people who want to ask.
There was, if you want, there is Julio has a question, and then if we have time, we come back to you, Roussos.
Yeah. Thank you.
Thank you very much for your question, but for your presentation. I have a question as about fracking, where you present the case for wells, but I'm still intrigued with the case for fracking. What we know about?
Yep. So, well, there's methane emissions and groundwater impacts and air quality impacts from fracking. So what do we know about them? We know that they are sources of methane, and they have, so for example, all the like US EPA and ECCC, they've done a lot of revisions to their methodology to better estimate emissions. One of the big sources is with this, same as with the urban, there's a lot of issues with spatiotemporal variation and these abnormal, so all of these emissions follow what are called extreme distributions with few sources contributing to most events. So it's trying to capture those large events is a real challenge. You need to do a lot of different screening and measurement activities. So, so in that sense, so that's one thing that we know, that natural gas systems, conventional and unconventional, and largely driven by the interest in unconventional, that they're driven by these abnormal events. If we link it back to abandoned wells, there are lots of concerns about, interactions with abandoned wells and, unconventional development. It's really hard right now to link those two because there's not enough data. And so our preliminary analysis, we didn't find any statistical relationship, but it may just be because we didn't sample enough.
Thank you very much.
Thank you, Julio, for the question, and Mary for the answer. So Roussos, we can come back to you for your second question.
Yeah, I'm somehow familiar with what is called smart fields or smart oil fields, and the use in this kind of high-end research of optimization and machine learning type methods and so on and so forth on different areas and aspects. So I'm wondering, how do you see operations research, various machine learning or reinforcement learning methods and so on being related to the work you have been presenting us today?
Yeah, so there's several aspects. So, if I go in order of what I presented, one is how many wells are there? A question like that, so we do a lot of data mining exercises in Canada and the US where we have data sources, but in some places we don't have that. And then even in Canada, US, there are regions where you don't have that. So, so machine learning, especially image analysis, to figure if we can see where the wells are. That is an active project that I'm working on. And then, so that's using machine learning. And then the other one is this question about which attributes are linked to the highest emitting wells. So we've, so far we've been really building the database so to apply these machine learning models. So there have been some good work done in this space of active well integrity. So these are not abandoned wells, but these are active wells, and which wells are likely to be leak. And they've used various types of kind of more like categorization type models, like random forest, neural networks. And so that is the approach that we're going towards. Right now, what we're trying to do is get that data. So we have, if we go back here, so there's all these different types of data, trying to put that all together for Canada and the US in a usable format so that we could put it into these machine learning models. That's where we're at right now.
Okay, thank you.
So Thank you, Rosos, for the question and Mary for the answer. We have another question from Ali. Please go ahead.
Thank you. I want to continue this slide. Just I see the factors that you are considering to monitor for wells. Do you also consider like the completion of the wells, you know, the integrity of cementing and the gas that may escape and leak from behind the casing? But the picture that I saw, there is no pressure sensors or pressure gauge to know how much gas is behind the casing. Even inside the wells, there is no pressure gauge. So they are very old. So the integrity of the wells most probably have been deteriorated over the years. So there is high probability of escaping gas behind the casing.
Yes, that's totally true. So for when you have active well, then we have the you could look at surface casing pressures. That's typically what in the US. In Canada, you can look at surface casing vent flows to get a good sense. What happens when you abandon? So after, especially if it's been plugged, you don't have the infrastructure to be able to do those kind of tests. So so it works for up to like sometimes suspended wells, but it really depends where you are, because so if you have the infrastructure, yes, these tests are very helpful and useful. And in Alberta, for example, you have some of this kind of information, but not for wells that have already been abandoned or plugged. You don't have this information anymore. So you do have some information during its productive life. Maybe you can look at production, and those are some things that we're considering. But for a lot of wells, so if you want to look at just some regions, you might have the data. But what you would find that if you want to look for Canada and the US at that scale, then for most locations, you don't have that full data set. So we've looked at kind of, so even for depth, we have to actually use like geospatial analysis and other assessments to estimate the depth, because you don't necessarily have that information. So yeah, I completely agree. Getting that information would be helpful, and the active well integrity probably says a lot about abandoned well integrity, which is likely to be worse than active. But the big issue is getting that data.
That's right. Do you also consider like the formations that may be active for that abandoned well, using the neighboring active wells, you know, using the active wells to know the formations that may be producing this gas behind the casing, or they may leak inside into the wells because of the loss of integrity of the wells? Do you consider comparing the active wells with abandoned wells with the neighboring wells?
Yeah, so what we did find with well integrity, so there's a good study being led by the National Energy Technology Lab, and they're also use, and I'm starting to collaborate with them as well. They're also using a lot of machine learning to assess well integrity data. But there's not a clear, I mean, there are some trends, but it's really hard to, say, okay, even in a given field, and all the wells should be kind of the same vintage and same kind of technology, you get a huge variation in integrity. You could still get a huge variation in integrity. And if you measure methane emissions, you get orders of magnitude variation. And so and also in a given field, if you have one that's plugged and unplugged, you get a very different number. So yes, that is a possibility, and it requires looking into more in detail. There is evidence for geographic variations playing a role, as I mentioned before. So which can be embedded, which with what you said is kind of embedded in that. We have used that kind of information for geochemistry. So if you can figure out what's the makeup of the gas coming from certain formations, if you know that, and then you find another leaking well, and then you see the geochemistry, then that can give you an idea of where that gas is coming from.
Thank you.
Thank you, Ali, for the question. Thank you, Mary, for the answer. Do we have any other question or comments? If not, thank you again very much, Mary, for your very interesting presentation.
No problem. Thank you.
Thank you all for your participation.